Okay, so in this video I want to talk about writing whole numbers using bases other than base 10. So we'll definitely talk about base 2 because I know, certainly base 2 has a lot of uses in computer science. So I imagine, a fair number of you watching this will probably be watching it because of that. But then we'll also look at some other bases too because there's some other interesting things going on. So this will probably be a slightly longer video. I wish I had more time. I might even go into some more of this later because I thought it was interesting. So here's the game plan. And so when I started thinking about this, somebody requested doing this video, and I thought, I honestly have never really thought about this too much. Like, I never was taught how to do this in school, but I thought, can I sit down and figure this out? So here are some things, I want to point out some things that I discovered when doing this. And, okay, so the first thing is we're going to talk about base 10 a bit more. And again, base 10 is just what most of us, well, I think it's what all of us have always used. And it's kind of interesting to sort of wrap your head around some of these other bases. So I'm going to point out a few common threads that relate things together to make it a little more systematic. We'll look at base 2 in a bit more detail, do a couple examples. We'll do some other things. I think I picked base 5 at random. We're going to look at base 12 as well because that is actually, I think, a more interesting base. And then we'll just, so some of the examples, we'll look at converting whole numbers in base 10 to other bases and vice versa. So we'll just do some basic examples. Okay, so here we go. Okay, so, again, I don't really think most of us really think about what we're doing when we write a number in base 10. If we write the number 926, what does that mean? Well, it means, right, you have 926 things. So, okay, that's a little redundant, right? But let's really look at what we're doing. So, let's look at that number 926. So, of course, this is stuff you see in elementary school. The 6 is what we say, that's in the ones place. The 2 is in the tens place. And the 9 is in the hundreds place, right? We have 9 100s, 2 tens, and 6 ones. And if you think about it, we can write, the hundreds as our base, which is 10 to the power of 2. We can write the tens place, well, that's our base, which is 10 to the power of 1. And the ones place, well, 1, that's just 10 to the power of 0. And we're going to see this theme crop up over and over again. And that's why I'm kind of pointing it out. The columns are going to represent the base raised to the exponent of 0, the base raised to the exponent of 1, the base raised to the exponent of 2, etc. The base raised to the exponent of 3 if you have a larger number. And so again, our base is appearing here. That's what I'm trying to point out. So, and what I said just a second ago, I want to say that again. The number 926, what does that mean? Well, it means we have 9 100s, we have 2 tens, we have 6 ones, or again, writing this using our base, we have 9 of our base 10 to the power of 2, we have 2 of our base 10 to the power of 1, and we have 6 of our base 10 to the power of 0. And when we mean 926, what it means is we have 9 100s, which is 9 times 10 squared. We have 2 tens, which is 2 times 10. And we have 6 ones, which is 6 times 10 to the 0 power. And if we add those together, we get 926. That's what we mean when we write the number 926. Okay, you're like, all right, Patrick, I know this. So we'll start looking at base 2 here in just a second, but I want to point out something real quick. So when we use base 10, we're only using the digits 0 through 9, right? Those are our symbols that we use, 0 through 9. When we write a number like 10, well, we're really just using the digits 1 and 0. When we use base 2, we're only going to use the digits 0 to 1. And for example, for base 5, well, we're only going to use the digits 0 through 4. Now, my last one's really not quite true, but hopefully you'll get the gist of what I'm saying here. For base 12, we'll use the digits 0 through 11. Well, not quite. We're going to have to introduce some new symbols for that. We'll see here in a moment. But let's just make up some random examples here of numbers in different bases, and then we'll just convert back and forth. So let's look at something using base 2. So let's look at the number let's just say, I'm going to make a number at random. So let's do 1, 0, 1, 1. So if this is in base 2, what number, so I want to know what is this number in base 10. And base 10 is also called decimal. So we could say, what is, if this number 1011 is in base 2, what is this number in base 10? So suppose a computer, right? Computers just use ones and zeros. If a computer ran across this and would want to interpret it, if we wanted to interpret it as a number in base 10, what number is that? Well, again, what you can think is, okay, so here's our number, 1. I'm going to just make a little column like a second ago, 0, 1, and 1. Well, let's think about our base. Okay, again, we're using base 2. So this is going to be 2 to the 0. This is going to represent 2 to the first power. This is going to represent 2 to the second power. And this is going to represent 2 to the third power. So we don't have, just like a second ago, right? A second ago we had the ones place and the tens place and the 100s place. We don't have that anymore. Now we have the ones place and the twos place and the 2 squareds place and the 2 to the third powers place. And what we'll do is we just do the same thing. We basically just add those numbers together. So this number 1011, it says really we have 1 times 2 to the third. So we have 1, 2 to the third. Plus we have, well, 0 of the 2 squareds. We have 1 of the 2 to the firsts. And then we have another 1 of the 2 to the zeros. Well, if we convert that, well, 2 to the third, that's 8. Well, 0 times anything is 0. We'll have 1 times 2, which will be 2. We've got 1 times 2 to the 0. That'll be 1 times 1, or 1. So 8 plus 0 plus 2 plus 1, that's going to be the number 11. So the number 1011, that's going to equal the number 11 in base 10. Likewise, we could write the number 11. If somebody said, how do you write the number 11 in base 2? Well, it would be 1011. So let's show how to convert. Let's look at an example of taking a number in base 10 and rewriting it in base 2. So let's write the number, and again I'm just making up a number at random here. Let's look at the number, 53, and we're going to assume this is in base 10. So let's write the number 53, which is in base 10, as a number in base 2. Okay, so what you want to do is you want to find the largest power of 2 that would go into 53 without going over. So that's going to be the first sort of game plan here. So let's write down some powers of 2. Well, 2 to the 0, we said that's 1. 2 to the first, that's 2. 2 squared, that's 4. 2 to the third power, that's 8. 2 to the fourth power, that's 16. 2 to the fifth power, that's going to be 32. And 2 to the sixth power, that's going to be the number 64. So let me give myself a little more room here. Okay, so the largest number that would go into 53, the largest power of 2 would be 2 to the fifth power. Okay, so let's see. So we've got 53. We can write that as 2 to the fifth power. Okay, well, 2 to the fifth power, we said that's 32. So let's see. 53 minus 32. That's going to leave us with 21. And now we do the same thing with this remainder. We think, what's the biggest power of 2 that will go into 21 without going over? Well, it looks like, okay, 2 to the fourth, that's 16. Again, 2 to the fifth is too big. So if we use 2 to the fourth, okay, so now I've got the number. So far I've got 32 plus 16. Well, again, okay, if I take 21 and I subtract away 16, that's going to leave us with 5 remaining. So I'm going to do the same thing. I'm going to think, what's the biggest power of 2 that will go into 5 without going over? Well, 2 squared, 2 squared is going to give us 4. So again, we can subtract away 4. So now we've just got 1 left over. Well, the largest power of 2 that would go into the number 1 without going over would be 2 to the 0. 2 to the 0 power. So just like a second ago, if you think about, making this little column, so I'm going to make one of these here. So we've got 2 to the 0, we've got 2 to the 1st, we've got 2 squared, we've got 2 to the 3rd, we've got 2 to the 4th, and we've got 2 to the 5th. Well, let's see. We've got 1 2 to the 5th, we've got 1 2 to the 4th, we have 0 2 to the 3rd powers, we have 1 of the 2 squareds, or 2 to the 2nd power. There's no term involving 2 to the 1st power, so we've got 0 of those. And last but not least, we have 1 of our base 2 to the 0. That's going to be the number 53 now in base 2. It's going to be the number 110101. That would be the base 2 representation for our familiar number 53. Okay, so that's base 2. That's how you go about doing base 2. For those of you that want to see more of these, leave a comment in the video, and I'll happy to go over some more of these. But this is the basic idea. Excuse me. So I think I said let's pick a number in base 5. One other thing I want to point out as well. One other thing that I think is interesting. In base 2, what does the number 10 represent? Well, again, if we think about it, that means we have 0 times 2 to the 0 power, plus we have 1 times 2 to the 1st power. So again, if you think about making our columns, this is the 2 to the 0 power, 2 to the 1st power. So it says we have 1 of the 2 to the 1st powers, 0 of the 2 to the 0 powers. Well, we get 0 plus 2 gives us the number 2. No matter what base you're using, the number 10, or I shouldn't say 10, 1, 0, that's going to always represent whatever your base is. And, okay, maybe that should be obvious if you think about it, but to me, at first, it just kind of, that to me somehow is a very pleasing, I don't know, I find it very satisfactory, or very satisfying, I should say. So hopefully you'll find it interesting too. So I said let's look at a number in base 5. So let's do the same thing. I'm just going to do one of these. Let's look at a number in, so this is a number in base 5. So again, we can only use the digits here 0 through 4. So let's convert from our number that's in base 5. I'm going to use 4, 2, 0, 3. And I want to think, okay, so here's our number in base 5. What is this number in base 10? Well, again, it's just going to be the same thing. I'm just going to do this little column trick that I did. So we've got 4, 2, 0, and 3. Let's see. So I think I was putting my bases above the numbers. Okay, so here it is in base 5. So again, this first digit on the very right, that's going to represent our ones place, the 5 to the 0 power. Then we've got 5 to the 1st power, 5 to the 2nd power, and 5 to the 3rd power. So in base 10, it says we've got 4 of these 5 to the 3rd powers, plus it says we've got 2 of these 5 to the 2nd powers. Well, it says we have 0 of the 5 to the 1st powers. And last but not least, it says we have 3 of the 5 to the 0 powers. Let's see, so 5 to the 3rd power, recall that that's 125. So this is 4 times 125, plus 2 times, well, 5 squared is 25, plus 0, plus 3 times 5 to the 0 power, which is 1. So let's see, 4 times 125, I guess that's going to be what, 500? Plus 2 times 25 will be 50, plus 0 plus 3. this would be the number 553 in base 10. So the number 4203 would be, in base 5, would be equivalent to the number 553 in base 10. Okay. So let's jump now. Let's do one more. Let's look at base 12 now. Maybe we'll just do one more example of this. So base 12, and base 12 actually has some interesting uses. There's some pretty hairy arithmetic that's related to all this stuff, which again, I don't know that many people probably need this in their real life. But if anyone's interested in seeing more, I would love to try to understand it a bit better myself. So okay, base 12. So okay. We said whatever base you're using, you have to use digits that are smaller than that. That was kind of what I was trying to allude to at the beginning. So for base 12, we're going to use the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, I can't write 10 because 10 only makes sense with our base 10. We need a new symbol to represent the number 10. And there's actually some different symbols that people use. One of the symbols they use is like an X, which, you know, if you remember from Roman numerals, the X represents the number 10. So this represents the number 10. This is going to be our familiar equivalent number 10. To get the number 11, again, there's some different ways they write it. I think the way, the way that I saw them using it, it was an upside down, let's see, which one was it? Oh no, I've forgotten now. Oh no, I forget what they used. I should have wrote this down somewhere. They either used an upside down 2, or they were using an upside down, or a twisted 3. I think it was the upside down 2. So that's what I'm going to use here. And hopefully this is correct. So again, there's some debate on this. Certainly go check this out. I think this is what they use. I think this is used to represent 11. I had it and then I forgot it. I was looking at this yesterday. So you can double check this. It doesn't matter. I mean, it does matter if you're really interested, but that'll be kind of a minor detail. So let's look at maybe one more example. Let's do one last example. Let's convert. So suppose we have the number, so the following number is in base 12. And we want to know what number this is when we convert it back to our familiar base 10. So let's just pick out some numbers at random. So let's use the new symbols, right? Because those are kind of exciting. So there's the X, and again, I forgot even what the names of these symbols are. So I'm just going to call it X and upside down 2. So let's throw an X in there. Let's suppose we've got a 5, our familiar 5. Let's throw an upside down 2 in there. And let's throw one more digit in there. How about, I don't know, how about 4? Okay. So, same trick. I'm just going to write down the powers of 12. And there's definitely proponents for using base 12. There's actually a whole society, there's a whole group dedicated to using base 12 in the United States and elsewhere around the world. I didn't know that. So, there are some big advocates for base 12. Okay. So we've got our columns. We've got 12 to the 0 power, 12 to the first power, 12 to the second power, 12 to the third power. So there's our X, our 5, there's our upside down 2, and there's our 4. So let me put this off to the side. Let's see, what is 12 to the third? I don't even remember that number. I've got my calculator off to the side here. So let's see, maybe I should know that. So 12 squared, I know that one. That's 144 times 12. Let's see, so 12 to the third power, that's going to be 1,728. 12 squared, that's 144. Well, 12 to the first, that's just 12. And 12 to the 0 power, that's just going to be 1. So when we rewrite this number now in base 10, so let me find one more piece of paper. So in base 10, Okay, so our value here, our x, we said that's going to represent our familiar number 11. So it says we have 11, 12 to the thirds, plus our next number here was 5. So then it says we have 5, 12 squareds, plus, then it says we've got our upside down 2, which represented the number, oh shoot, okay, sorry. I got ahead of myself. Our x represents 10, not 11, excuse me. So let's do this one more time. That's why I wrote them out. I'm not familiar with these symbols. I should again remember the x at least. So it says we've got 10 of our 12 to the third powers, plus 5 of our 12 to the second powers, plus, okay, our upside down 2, that represents 11. It says we have 11, 12 to the first powers. And then it says we have 4 of our 12 to the 0 powers. So, okay, so we said 12 to the third power, that was 1,728. So if we multiply that by 10, we're going to get 17,280. Let's see, so we said we've got 5 12 squareds, so let's see, 5 times 144, I'm going to again do this off to the side, 5 times 144, that's going to be 720. Let's see, 11 times 12, that's 132. And then we have 4 times 12 to the 0, which is just going to be 4. So again, I'm going to be lazy here. So 720 plus 1,700, 280, plus 132, of course, plus 4. Shouldn't really need a calculator for this. 18,136 in base 10. So again, this number, which was in base 12, this number, which is in base 12, is now going to be equivalent to the number 18,136 in base 10. So, okay, I think I'm going to leave it there. Hopefully you see the general idea of how to convert from a number in one base into base 10. We only did one example where I wrote a number in base 10 into the other base, and that was the one using base 2. But if you need to see any more of those, let me know. I mean, we can do some of those pretty quickly. But again, it's basically that idea of you're trying to find the largest power of the base that will go into that number without going over it. You know what? Let's do one more. Let's do one more because it's fun. So let's write, just to be complete here, because otherwise I'll feel like I've left something out. Let's write the number. Suppose we have the number... Let's see, let's use the number, let's see, what's a decent number? I don't know, let's use 176. So the number 176, and let's suppose that's in base 10, and let's write it in base, let's write it in base 5. Okay, so again, 5 to the 0, that's going to be 5 to the 0, that's going to be 1. 5 to the first power is 5. 5 squared is 25. 5 to the third is 125. And any power larger than 5 to the third is definitely going to be bigger than 176. So I'm going to do the same thing. I'm going to think, okay, right, because once we get to 5 to the fourth, if we multiply that by 5, what is that, 625? Okay, we're already too big. So 176. The largest power of 5 that will go into that is 5 to the third. So I would need 5 to the third, and I'm going to do the same thing. I'm just going to subtract. So 176, if I subtract away 5 to the third, which we said is 125, that's going to leave us with, what, 51? Okay, so now I do the same thing. I think, what's the largest power of 5 that will go into 176 without going over? Well, it looks like 5 squared is going to be the next one. But notice we can actually use 2 multiples of 5 squared. So I can only use the digits 0, 1, 2, 3, and 4 when I write my number using base 5. But I can actually use 2 multiples of 5 squared. So 2 multiples of 5 squared, right? Because if I just used 1 multiple, If I just used one multiple, that would be 25. I would still have 26 left over. Well, that means I could have actually used a second multiple of 5. So, okay, 2 times 5 squared, that's going to be 50. So if I do 51 minus 50, that's going to leave us with the number 1. And we said to get the number 1, we just use 5 to the 0 power. So we would have 1 of 5 to the 0 power. So again, if you add up the numbers on the right, that gives us 176. So let's think about our columns here. We've got 5 to the 0, 5 to the first, 5 to the second, and 5 to the third. So we said we had 1 5 to the third. We had 2 5 squareds. We have 0 5 to the firsts. And we have 1 5 to the 0 power. So the number 1201, which is in base 5, that's going to be equal to the number 176 in base 10. Okay. All right, I'm going to stop there. So again, hopefully these examples make some sense. And yeah, you know, some of the stuff I really haven't quite figured out or thought about too is like how to use decimals. There's probably interesting things about divisibility and prime numbers in different bases. There's obviously some applications. I mean, people have used base 12. I mean, look at how Americans measure, you know, feet, for example. We use 12 inches. You know, think about, you know, the clock. So anyway, okay, so I'm going to stop there. Again, hopefully you found this interesting. If you want to see some more, just let me know. I'd be happy to talk about it some more.